which are called negative resistance devices. So usually all the devices that we have learned so far, starting from simple resistance capacitor to
Sorry.
diodes, then
Excuse me, ma'am.
yeah.
Yeah, ma'am. I'm sorry, I'm interrupting, ma'am. Actually, could we get the MOSFET slides, ma'am? Because it's getting a bit difficult for us to study from just the recordings, because the written
Okay, I will
material.
share it. I will share it. Okay,
Thank,
fine.
thank you, ma'am.
I will
Thank you
share
so
it.
much, ma'am.
Okay. Okay. So yes, so I was talking about negative resistance devices, and so usually the devices that we had, even MOSFETs, right? We studied them. So usually when we draw the IV characteristics of any such device, what we see is that current and voltage are kind of in sync in this perspective, that if voltage increases, the current also increases. The way it increases could be different. Sometimes it can saturate, but we never ever have seen a device where the voltage is increasing but the current is decreasing. That is the slope of that graph of IV characteristics of any device we have not seen yet, where the graph is a falling slope. Okay, so that we have not seen yet. So in this particular module, we are going to discuss about these devices and negative resistance, so to say, or negative differential resistance. We say we mention it as negative differential resistance sometimes, because in these devices, because the curves are nonlinear, we don't define resistance by simply saying it is V is equal to IR from that equation, but we take a differentiation or slope of that graph. Okay, so from there we define resistance. So in this particular devices, let me just share my screen here. So in this particular devices, you will see that not the entire IV characteristics definitely, but a portion of that IV characteristics is going to show a slope which is not a positive slope. So we are going to have a negative slope in at least a portion of these devices. So there are three different devices that we will discuss in this slot, and the first in the series is tunnel diodes. So you will see that all these three devices, tunnel diode, gun diode, and IMPAT and TRAPATs, that we will discuss at the very end, you will see that they all have these negative resistance regions in their IV characteristics, but the way that it comes into the picture, the working principles are completely different. So one by one, we will talk about this device, and the main essence of this particular module is to understand that how beautiful different physics can arise when you as you just tune your semiconductors a little bit and try to see that what kind of properties can arise from there. So today we will discuss about tunnel diodes. Let us start our discussion. So as I already said, that negative resistance means when the curves will be having a negative slope, right? So what you will see is that in this particular devices, including tunnel diode, if you draw the I versus V graph, you will find a portion where the curve is usually falling. But this means a negative slope, right? So here you have a differential resistance. If you take a differentiation of this line, you will get a negative slope. Okay, so this region is the negative resistance region of that you will see. So usually what happens is in these devices you have this some way or other it is similar to an S. Okay, so either a S sitting straight like this, or a rotated S like this. So the curve of the IV characteristics looks like an S. Okay, where you have this change in slope lying in between. So this is the region where the negative resistance arises. So why that happens and how this particular tunnel diode, how that device looks like, let us talk about this. Okay, so tunnel diode was first invented by Leo Esaki when he was just completed his BTech and started doing his PhD. And that device, that first experiment that he has done, basically finally resulted into a Nobel Prize in 1973. And this particular device is still being used in various applications around the world, and the simplicity of its construction is really amazing. So what is the for how this device is different from usual diodes that we have? Almost nowhere. It is basically a p-n junction, okay? Just a p-type and an n-type fused together, exactly like your p-n junctions that you have already studied in detail. You have studied its band structure, depletion regions. You have become experts of these things by now. But the only difference that I have in case of tunnel diode is that here both the p-type side and the n-type side are really highly doped. That's it. That is the only difference you have. Okay. So p-type and n-type side, both the sides are quite highly doped. So what is this percentage of doping? How high is the doping? So usually I guess you know that the p-n junctions that we make for our diodes, they have this 1 in 10 to the power 8 doping, right? Impurity doping, that for 10 to the power 8 pure atoms, you dope one part of impurity. So here in case of tunnel diode, you will have a p-type and n-type where it is 1 part in 10 to the power 3. Okay, so for only 1000 atoms, you are having one atom of impurity. So that is a huge amount of doping. It's heavily doped. Okay, so by now you have already understood that how the depletion width of any junction is dependent on the level of doping, right? You have already seen that because if you dope really high, then in a small region, if the depletion region forms, the potential will be high enough to stop the flow. And that means that if I have a heavily doped p-n junction, it will have a really thin depletion region. Okay, and this is basically the key to understanding the entire principle of tunnel diode. Because when you have a device like this, something called quantum mechanical tunneling takes place in these devices. Okay, so today I will try my best to, without any mathematical details, just try to convey the idea of quantum mechanical tunneling to you so that you can understand that how a tunnel diode works. Okay, so let us take baby steps towards this direction. This is the symbol of tunnel diode. This is how we denote a tunnel diode in a circuit. Okay, so it's generally made of germanium. So let us see that how the band structure gets changed if I increase this doping level. I change this doping level compared to the normal p-n junction. So I guess you are familiar with this curve, this picture that I have here, this figure that I have here. This is the p-n junction diodes band structure. So are you familiar with this graph? I guess sir has discussed these things enough in your class. Okay, so this is basically the p-n junction where you are just seeing that the conduction band and valence band on both sides of the junction. Okay, so if you don't have any battery connected across the p-n junction, that means your Fermi level will be same for both p-type side and n-type side. So it will be in an equilibrium, right? So we know that the Fermi level is very close to the valence band in the p-type side because there has been some doping, right? Similarly, the Fermi level is going to be very close to the conduction band in the n-type side. So if I have a p-n junction, then the band must have a structure which is bent like this to maintain the Fermi level same on the both sides of of the junction. Okay, so now just imagine this simple picture and try to imagine that what happens if this is suppose a normal p-n junction, okay, and now I start doping more and more on both sides. So what will happen to the Fermi level? What do you expect? The Fermi level will go more close to valence band in the p-type side, and it will move more close to conduction band in the n-type side, right? And what will happen beyond that? If I further increase the doping, then what will happen? What do you think?
And the levels will enter the bands.
The level will enter the bands. Very good. So that there is no other way, right? So there is the only way that I can maintain the equilibrium, and I am going in a crazy level of doping where the doping is really high. Then what is supposed to happen is something like this. So this is the band structure or the band diagram in case of a really highly doped p-n junction like tunnel diode. That this is the top of the valence band, but the Fermi level is inside that. And this is the bottom of the conduction band, and the Fermi level is inside that, but it is same on both sides because there is no battery attached yet. Okay, so both sides, the Fermi level is exactly at the same level because the battery is not attached. So there is the entire thing will be, but the Fermi level will go inside both p-type and n-type material. They will go inside the respective bands. So this particular kind of materials where you have this really highly doped materials, you call them degenerate semiconductors. So in degenerate semiconductors, what happens is not only the electrons but the dopant atoms are also have started interacting with each other. Okay, and this is the key to formation of bands. You know that, right? That the electrons lose their identity, they forget that which particular atom they belong to, and that from there the picture of bands come. And here the dopant atoms are also interacting with each other, and thus you have these Fermi levels inside your valence band or conduction band, depending on it's an n-type or p-type semiconductor. Okay, so with this idea that the Fermi level will be inside the respective bands, now let us now see that what happens if I now attach a battery and forward bias my junction. Okay, so in normal PN junctions, we know that if I attach a battery and forward bias it, what happens in the band diagram? You can imagine that the battery will help the electrons to climb that slope. Okay, so the battery is helping the electrons or the holes to climb this hill. Okay, so this is also a hill for the holes because they are positively charged, right? So this pink line is also a hill for the holes on the p-type side. Similarly, this green line is basically the hill for the electrons. And the energy from the battery that we are supplying, the force from the battery that is coming into the picture, is basically helping the electrons to climb through that hill and reach on the other side, and thus current flows. Okay, thus current flows when I attach a battery in a forward bias mode. Okay, that is how a normal PN junction works. So if you just imagine this in terms of the barrier potential, so you know that there is in the depletion region, in one side I have positive ion sitting, on the other side we have this negative ion sitting. So there must be a barrier potential that has been developed there, right? So how the electron flow starts? The electron flow starts only at a certain voltage where the voltage is strong enough so that the electrons can cross this barrier. Okay, so the electrons have to have enough force, enough energy from the battery provided, so that they have enough energy to at least crawl through this hill, right? So they have enough energy just to pass through this barrier and reach on the other side. That is why there is a term called cut-in voltage in our normal ordinary PN junction diodes, right? In germanium it's 0.3 volt, in silicon it's 0.7 volt. Up to that voltage there is no flow of current. So that voltage basically signifies that how much barrier potential is there, how much steep this hill is, so that you understand that at least this much voltage you have to provide for the electrons to climb through that hill to cross this barrier. So this is how a normal junction diode works, right? So we understand that this is how a normal junction diode works. This is how current flows in normal junction diodes. So for first 0.3 or 0.7 volt, someone is switching on and off their mics. Please keep it off. Please keep your microphones off. It might be disturbing others. Okay, so in normal PN junction diode, this is the characteristics that we expect, that if I increase voltage from 0, then for first some amount of voltage, 0.3 or 0.7 volt, there will be no current flow because there is a barrier potential to overcome. And after that voltage, the current flow will start because the electrons will now first crawl and then climb through this hill, pass through this barrier, and the excess energy will help them flow, cause the barrier potential and flow. So this is how a normal junction diode works. Okay. Now what happens in tunnel diode? To understand that, we have to understand that what is tunneling. So in case of normal junction diode, the main thing to understand is that the energy of the electrons have to be greater than the barrier height or the barrier potential, right? So this is the key understanding, that the take-home message from the discussion that we had so far is that in normal junction diode, the energy of these electrons have to be higher than this barrier potential. But quantum mechanical tunneling says that there is a certain probability that you can reach the other side of the barrier even when your energy is a bit low of the height of the barrier. So it's kind of saying that let us just imagine that your friend is standing on one side of the wall and you are standing on the other side of a wall, and the wall is quite high, okay, and you have a ball in your hand and you are trying to throw that ball so that it can reach your friend. Okay, so this simply means that you have to have enough energy provided inside that ball so that it can climb this height and cross the wall. If that energy is less, then it cannot cross the wall. So this is our physical understanding, this is our physical world, and that is how it behaves in normal junction diodes. Okay, but quantum mechanical tunneling says that it is possible that you can reach the other side even if your energy is low. So the energy of this ball does not has to be higher than this particular wall. There is a certain probability that it can still pass through and reach this particular person. How? So what is the basic understanding of quantum mechanics that you have learned? So basic understanding of quantum mechanics is the wave particle duality, right? So let us just think about it from there without any mathematics. Let us try to understand tunneling. So that simply means that if I think this picture, this same picture in terms of a wave, okay, so this ball is not a ball anymore, and just imagine that your friend is calling hey from the other side of the wall. So this is a sound wave now. This is not a ball, but the person is saying something. The person is singing a song or whistling. Okay, so this is quite clear, right? So if the wall is quite high, that does not stop this sound to reach the other side of the wall, does it? It does not stop it, right? Because it's a wave now. For a particle, it is really hard to cross this wall and reach the other side if the energy is not sufficient. But for a wave, the theory is a little bit different, right? For what is the understanding for waves? So what will you say that if I am standing in one side of the wall and you are on the other side, what is the thing that matters for a wave to reach the other side? That is the thickness of the wall, right? If the wall is really, really thick and the person is calling at a constant intensity, then that intensity will fall down if the wall is really, really thick. Okay, so the sound that reaches the other person on the other side of the wall will be faint and faint and faint as you go on increasing the width of the wall. So it does not depend on the height of the wall anymore, right? Right now it depends on the width of the wall. So if I am considering that this particular electron or this particular ball is basically now identifiable with a wave, then there is a certain probability of that particle to reach the other side in form of a wave if the wall is really thin. So is this concept more or less clear? Is this idea more or less clear? Do you understand at least the idea of quantum mechanical tunneling, what I'm trying to say?
Yes, ma'am.
Okay, so very good. So let us just talk about it. So classically that means that the carrier must have energy at least equal to the potential barrier to at least crawl through, right? But in quantum mechanical particles, what is needed is that the barrier has to be really, really thin, and then there is a certain probability, of a phenomena called quantum mechanical tunneling if the barrier potential is really thin. And that is what happens in tunnel diode. If the depletion region is really thin, that means the width of this potential barrier becomes really thin. And this opens up a possibility of tunneling through the barrier for these electrons. So let us see step by step that how the current flows. If I start now attaching a battery around this tunnel diode device, where it is a simple PN junction just with a very highly doped p-type and n-type side. Okay, so let us see that what happens if I start going in this direction, increasing the voltage step by step, what happens to this picture of my band diagram and how tunneling can take place here. Okay, so at zero bias, when there is no voltage across the PN junction, the Fermi level has to be at equilibrium on both sides because they are highly doped. So we have already concluded that they will be inside the respective bands. The Fermi level will be inside the respective bands, but they will be seen on both sides. Okay. So here the interesting thing to see is that the electrons and the holes are not being able to see each other. See each other means that the holes are basically empty states, right? So electrons will crave to reach these empty states if they can see it, but here the Fermi level ends, so that these states are not visible to these electrons. If these states are here, somewhere here, so if these states are somewhere here, these holes are somewhere here, then the electrons can see them. And due to this affinity, if this potential barrier is really thin, there is a probability of tunneling. Okay, so right now the holes are here and the electrons are here, and there is no way that the holes can see the electrons. Here is no electrons here. I don't see any electrons here, right? Similarly, these electrons cannot see any holes because there are no holes in this portion. Okay, so at zero bias, where there is no potential applied, no current can flow because the electrons and holes are not being able to see each other. Okay, see the empty states available for them. So holes are empty states for electrons and electrons are empty states for holes. They cannot see those states yet. So now what happens if I apply a small forward voltage? As soon as I apply a small forward voltage, that means that this level goes up a little bit, right? So you can consider any one side at zero potential and the other side going up or going down because I have applied a voltage, forward voltage. So that immediately breaks the equilibrium and the Fermi level, the equivalent position of Fermi level breaks down. And this, you can imagine that the p-type side went down a little bit or the n-type side went up a little bit, whatever you want. But as soon as this happens, these states, the electrons and these holes are now able to see each other. Okay, so there these electrons in the conduction band of N region, some electrons are there which are directly opposite to the empty state of the valence band sitting on the other side. So just imagine that two trains are passing each other, and you are sitting in one train at one window and your friend is sitting at the other train at other window, and these two you are continuously changing the voltage here, which means you are continuously sliding these two trains in two opposite directions. So there will be one time where the two windows start overlapping. Then after a certain time, there will be a portion where you have maximum overlap between the two windows, and then it will pass through, right? So something similar is happening here. As soon as you apply a small forward voltage, these states start seeing the empty states on the other side, and immediately, because of this very thin barrier potential, some tunneling starts occurring. The most interesting part here, no cut-in voltage. Immediately, as soon as you apply a small forward voltage, immediately a small tunnel current starts flowing, which is absent in normal PN junction diodes. This only happens because the barrier is quite thin here. So a small current starts flowing in due to quantum mechanical tunneling. Okay. So what happens now? Again, if I increase the voltage a little bit, at a slightly higher voltage, you can again imagine either the p-type side went down more or the n-type side went up more, and now these two states are completely aligned. So the maximum number of maximum alignment right now we have. So maximum number of electrons in the n region are sitting opposite to the maximum number of empty states in the p region. Okay, so that means maximum tunneling is occurring at this point. So huge amount of tunnel current will start flowing in the device, and this current will start flow. So in the IV characteristics, what you will see is that the current started increasing, and now it reaches a value where the tunnel current is maximum. Why the tunnel current is maximum? Because even after this point, if I increase the voltage a little bit, then again the alignment goes off, right? I have a slight misalignment. Again, this is a little bit more higher, and this is a little bit more lower, and now all the states are not visible. So the tunneling current starts decreasing now. So this is the key point where the negative resistance region begins. As the misalignment starts, the negative resistance region begins because the tunnel current starts decreasing, and you can see that the voltage is increasing, but the current starts decreasing. Okay, so this is the portion where I am entering the negative resistance region. But so what is supposed to happen now? The tunnel current is going to fall and fall and fall down to zero. But when the tunnel current falls, on the other side, the cut-in voltage has been crossed. And as the cut-in voltage has been crossed, So the tunnel current is decreasing like this. Okay, tunnel current is decreasing like this. Tunnel current is decreasing. Okay, but already the cut-in voltage has been crossed, and the current, the original current for normal PN junctions, that has already started increasing at a certain point during this time. So at a certain point during this time, the current also started increasing due to the normal forward current. Okay, so these two things meet at a certain point, and tunnel current falls down to zero, but the normal forward current starts flowing and the current increases once again. Okay, so this is how, where it is completely misaligned, but now the hill is quite less now. The steepness of the hill has become quite less now, and now the electrons can flow normally like a normal forward bias current. Okay, so the normal forward bias current increases and the tunneling current decreases, and they meet at a certain point, and after that the normal PN junction current, the normal forward current dominates, and the current starts flowing in a positive direction. So thus you have a shape of the curve which looks similar to an S. Okay, so this is the entire characteristics of tunnel diode. Let me just quickly introduce some nomenclatures. The maximum current that has been reached here is called the peak current. The voltage at which it happens is called peak voltage. Okay, the minimum voltage where the turning occurs, where the negative resistance region ends, is called the valley voltage. This is the minimum voltage that I get here. Okay, and the maximum current occurs once again when the voltage was increasing. Beyond that, the current can increase further when you have only the forward current flowing in the circuit. That particular voltage is called peak forward voltage. So peak forward voltage is a value where you cross, basically you reach the peak current value once again during increasing for normal forward current. Okay, so these are the different nomenclatures. This is called valley current. The minimum current flowing here is called valley current, and so on. Okay, so this is the basic characteristics of the tunnel diode, and you can see that between this VP, peak voltage, and valley voltage VV, you have this region where, though the voltage had increased from VP to VV, the current has fallen from IP to IV. So this region is called the negative resistance region of tunnel diode, and this occurs because of the falling tunneling current. Okay, so this is how it works. This is how a tunnel diode functions. This is the general working principle. Let us have a quick idea of the numbers. So usually you know that for germanium diode, 0.3 volts or 300 millivolt is the cut-in voltage. From there, significant amount of forward current starts flowing. But here you can see that around at 50 millivolts, the tunneling current is maximum. Okay, so around 50 millivolts, if you make a germanium tunnel diode, the tunnel current is maximum around at that value. Okay, so this is kind of a basic idea about the numbers of the valley voltage, the peak voltage, the valley current, and the peak current. Okay, so I will stop at this point for today, and I will give you some time to study about this and understand the phenomena of how a tunnel diode works. Okay, if you have any questions, you can ask away. Any questions?
Ma'am, I did not really get the part, ma'am, where after the negative resistance happens, like when we reach the valley voltage, how does it again rise up? I didn't really get that part, ma'am, because
just forget about the phenomena of tunneling and assume a simple diode. There also at some point the forward current would have started, right? So
okay.
Here simply the forward current starts and that picks up from that point.
Okay,
onwards.
so basically, basically the tunneling diode characteristic ends at the valley voltage. Like it stops
the tunneling
acting like a
behavior
tunnel
ends. The tunneling current ends at the valley voltage. Its contribution ends because beyond that point, the normal forward current dominates and it increases again, and resulting into this S shape. Okay.
Okay. Thank you.
Okay. So try to get the idea of quantum mechanical tunneling and how it is applied here, and several questions can be asked here, several conceptual questions can arise from here. So study it a little bit. If you have any doubts, let me know. And then we will meet at the time of the test then, because I don't have any class before that. So see you on that day then. Okay. Bye.
Ma'am, please
Thank you,
share
ma'am.
the slides.
Yeah.
Today's slides.
Yeah, I will share. I will share both the slides. I will share the MOSFET slides as well as this one. Okay.
Thank you so much, ma'am.
Okay. Sure.
Thank you, ma'am.
Bye then. Bye.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.